I'm very happy today to introduce, in principle, our webinar. My name is Arina Heinzig. I'm leading today this webinar, which is about the EO4SDG Mini-project and the Earth at Risk image contest, which is the award ceremony today. So this webinar is a little bit different as the usual one, where we have only one presenter. Today, we are celebrating the winners of the two contests that we have launched already in 2024. And we are presenting today, or the winner presents today, their results. I'm very happy today to have on my side a big team. The one place, these are the people which are presenting the winners itself, which we are celebrating today. And on the other side, I would like also to introduce Adnan Siddiq, who's today also here online and is helping me with this presentation of the ceremony and the awards. And I would like also to welcome Mohamed Khalil, who's in principle a representative of the IEEE Young Professionals. Okay, then just let us start. We have two parts today. The one part, as said, is about the EO4SDG Mini-projects, and the second part will be then led by the Earth at Risk image. For the Earth at Risk image contest will be led by Mohamed Khalid. Okay, let us start with the first one. So probably just also to introduce, so these mainly the presentation of the React. Team React is a technical committee at the IEEE Geoscience. And what we will do today, so we have in principle, we are a team of people which are trying to support people which are and to try to have also, let me say, a channel for them to discuss and coordinate their work and exchange itself in this framework using remote sensing data and looking for application-driven, let me say, application-driven methods in order to express things that are in principle available for the sustainable development goals. What we have here today, or what you see on the slides, is we have certain parts which we call local focused area, where we are focusing thematic on these regions. We have a team which is working on agriculture and food security. We have a team working on flood and water security, risk in high mountain Asia, in urban resilience and forest and mangroves, but also in the Pacific Islands. The goal actually of this local focused area is in principle to coordinate their work in the specific topics. The goal of the competition that we had, so our mini projects, which are for the Earth observation and the sustainable development goals, had different parts. In principle, the main part was to sketch a small science project using remote sensing data. And this is what the winners have done. And most of the participants today potentially have could be nice for them to see what is the outcome of it. The second is we would like with these mini projects also to motivate local students to work scientifically together. And we would like also to make aware of particular regional problems with these kind of mini projects. The outcome is today, in principle, the winning teams are presenting their results today here. And what is also as a second outcome, they will send a small summary of their work, will describe it, and we will publish it in the IEEE GRS magazine. Probably just to give a little bit an outlook of how many people have participated. We had around 23 submissions, and these 23 submissions have been done from different countries. So I'm very happy that we have a very, very good distribution. We have a lot of people coming from India. You see it already. We have somebody from Fiji, Ethiopia, Canada, Bangladesh, from Switzerland, South Africa, Pakistan, Italy, and Iraq. So we have a quite good distribution in terms of regional contest. And I would like also shortly to mention where are or who are the evaluation committee, and I would like to thank these people very much to dedicate their time to evaluate these proposals very carefully. As said, we have Professor Mohammed Adnan Siddiq from the Information Technology University, ITU in Lahore. Then we have Professor Deepankar Mandal from School of Agro and Rural Technology from Indian Institute of Technology in Guwahati. Then Professor Carlos Lopez Martinez from University Polytechnic de Catalunya, and Professor Rio Natsuzaki from the University of Tokyo. And myself, I was also doing this evaluation. Okay, and with this, we are switching now to the winners, and I'm really I would like to congratulate the winner for the third place, which is Nicolas Mitterrand. He's from the University of South Pacific, and he's also associated to the Australian National University. So he have in principle 2 affiliations. So congratulations to Nick. Unfortunately, Nick is in a time zone that is not allowing him really to participate today in person. However, he was sending us his recordings, and we are now showing the recordings here. The recordings will be around 15 minutes.
Good morning, everyone. My name is Nicholas Metherell, and today I'll be sharing about our project, Mineral Resource Extraction Detection, the MRED tool, and how this relates to the Earth observations for SDGs. This work has been made possible through the Pacific Community, or SPC, the University of the South Pacific, USP, as well as the Mineral Resources Department of the Ministry of Lands in Fiji. The project was also funded through the United Nations Development Programme. In terms of the outline for this presentation, I'll be covering the motivation for this topic and relevance to SDGs. I'll also speak a bit about Digital Earth Pacific and the Mineral Resource Extraction Detection tool. I'll then talk about how we've learned from some of the approaches in Digital Earth Africa, and also about our methods, including our machine learning approaches, some of the example results and outputs and change detection, as well as some of the wider applications of Digital Earth Pacific. Finally, I'll also cover our plans for future research and capacity development. So in essence, this project supports SDGs 14 and 15. So this project is all about monitoring mineral resource extraction, as well as its environmental impacts, both on waterways. So these include the in-river gravel extraction impacts, as well as the mining of other minerals and heavy metals in waterways, as well as on land. And so this supports the monitoring of aquatic and marine ecosystems, as well as terrestrial ecosystems. So this again supports SDGs 14 and 15. So for this project, we were tasked to develop an Earth observation tool to inform where monitoring and extension work should be undertaken. So this is a spatial prioritization tool to monitor mineral extraction activities. And this can be useful for monitoring both compliance and for enforcement in terms of areas where there are mining. We can enforce better regulation and have deterrents or penalties for mineral activities that are not licensed or permitted by the relevant authorities. And this can be used for both river and land-based quarries. So in order to monitor the impacts of the environmental degradation resulting from mineral resource extraction activities, we have to look at the symptoms. So some of these symptoms can include the impacts on river ecosystems when there is in-river gravel extraction, as well as the clearing of land for stockpiles and other facilities for mining. So these are some examples of a site in Fiji where we have the clearing of riparian vegetation. So that is the vegetation growing along river corridors and riverbanks, as well as the changing of the hydraulic channel itself. This can include the changing of the shape of the river and the geomorphology. We can also see impacts on water quality within the river itself. This can include greater volumes of sediment transport, turbidity, and other kinds of water quality disturbances. We can see greater erosion, leading to stream bank failure and stream bank collapse. And so these images show both before and after the establishment of in-river gravel extraction in this example of the Dawasamu River. And in developing this tool, we've been learning from some of our colleagues in Digital Earth Africa and Digital Earth Australia, and some of this work has been done on monitoring gold mining activities in Ghana. And this has been useful for us to see how Earth observation tools using similar infrastructure can be used to monitor mining activities. However, we were not able to directly apply this approach in contexts like rivers in Fiji, and this is because these contexts in Ghana are very large scale, continental scale, often terrestrial-based mining, where the methods involved mapping both the the confluence of new bodies of water as well as bare lands that are indicative of mining activities, because mining often requires a lot of water, so a lot of new bodies of water to help with the processes of the mining itself, the refining of the minerals and aggregates and metals, the cleaning of equipment for the mining itself. And so for our case, where we're actually looking at in-river gravel extraction in Fiji or terrestrial mines in Fiji, we do not always see large pools of water that can be monitored in the same scale as what has been done in Africa in this case. So we developed an approach that looked at areas of quarries, bare lands, and water, and then looked at the changes over time using Sentinel-2. And this work was done with collaboration with our team, including Alex Leith, who was one of our advisors in this process. And so in essence, what we've done is we've tried to classify both the bare lands class in brown, and this can include access roads, river banks that have been cleared of riparian vegetation, and other areas. And this is shown in brown here on the left. And then on the right side, we have the stockpiles or quarry class in red. And so this shows the stockpiles of aggregates and minerals here in red. And so we've developed a machine learning model based on training data to help us to identify these areas and spatially prioritize where further monitoring in the field needs to be undertaken. So we've moved away from our previous approach, which was a logistic regression model, which had additional noise and sometimes overestimated the likelihood of mining. to a random forest classifier, which has isolated some of the stockpile areas as shown here on the right. And again, this was also the case for coastal areas, and it reduced the confusion between bare lands and sand and beaches and mudflats with mining activities. So this is an example from one of the bauxite mines in Vanuatu in Fiji. And so as you can see on the left side, we have all of the different classes, land cover classes. And on the right side, we've just isolated in on the brown bare lands, the red quarries, and the blue water, pools of water, which again be used for the industrial processes and the tailings and other processes related to mining activities. This is another example that shows the Sambeto River. And again, moving away from a logistic regression approach, we used a random forest approach to identify both the quarry areas in red, as well as the potential in-river gravel extraction areas in blue. And so these areas are located close by to the stockpiles, which is realistic given our experiences observing these mining activities in the field. And so part of what makes this tool useful in monitoring ongoing impacts of mining is the change detection. So this is more for the temporal analysis. And so for this example here, we're looking at a gold mine in upstream of Sambeto. So we have this area of the quarry in red, the brown areas of bare lands, access roads, and potential areas of in-river extraction in brown, and the blue areas highlighting the river, as well as other surface water bodies. So in 2021, we saw the beginning of the establishment of these mining areas in orange. In 2022 to 2023, we saw the establishment of the stockpiles and the expansion of these mining areas. Another example is seen in the in-river gravel extraction, again in Dawasamu. In 2017 to 2018, we saw the expansion of these mining areas denoted in light brown and dark brown, where we had the expansion of mining areas. In 2018 to 2019, again, we see this area of mining expanding along the Dawasamu River. 2020 to 2021, again, some further clearing of land upstream. Now, in 2021, we see some regrowth of vegetation along the riverbanks. Now, we can monitor whether or not this regrowth is actually restoration as a requirement of the mining company, or this is a rehabilitation of the environment, or whether it's just the growth of shrubs and invasive species that have grown back, weeds that have grown back over the bare soils here. What's interesting is that in 2022, we see an expansion of mining further upstream in the river. So we're able to then use the license permit areas and then see whether or not these expansions of mining right up into the mountains are actually within the license permit areas or are outside of the license permit areas, which would make this mining activity in effect illegal. So these are some examples of the use of this MRED tool. This tool was developed through a process of an iterative process or a cyclical process in which we collect sample training data. We fit this training data to our satellite imagery and our also our elevation model, our SRTM or shuttle radar topography mission data, and then we use that to train a model. We then use that model to do a prediction or generate a classification over imagery, and then we do an accuracy assessment. After doing this accuracy assessment, we can work out whether or not we need to go and collect more sample training data to then help correct for mistakes or improve upon this model. And then we can repeat this model, repeat this cycle. And as we repeat this cycle, each time we go through this cycle, we'll make incremental improvements to the outputs. And so these are some examples of the training data and the outputs that have come out of it, the predictions. And all of this is made possible through the workflows and methods that are conducted within Digital Earth Pacific. So Digital Earth Pacific is a cloud platform, which is actually also a public technology infrastructure provided to Pacific Community or SPC members and others to be able to access petabytes of satellite data. And it also is used to generate regional Earth observations products. And so you can learn more about Digital Earth Pacific at www.digitalearthpacific.org. And Digital Earth Pacific was built upon the requests from member countries through a needs assessment consultation process where meetings were conducted with member countries in the Pacific to identify what were the main priorities and use cases for Earth observations or satellite data. And through this process, a number of tier 1 use cases and tier 2 use cases were identified. So through Digital Earth Pacific, we're able to work towards meeting many of these tier 1 and tier 2 use cases and needs identified in the Pacific that also align with the SDGs, as shown through this example of the mineral resource extraction detection tool for SDGs 14 and 15. And this is made possible through the computational capacity for scaling that's made possible through the public technology infrastructure of Digital Earth Pacific. And so what you're seeing here is the CPUs and the memory usage made possible through the parallel cloud computing capacity of Digital Earth Pacific. So in terms of our plans for the future, we hope to continue to make further improvements for this work through a third phase, to be completed at a later stage. And so this will include temporal segmentation, ideally through alerts and notifications of sudden changes in mining areas that can identify anomalies in these water, bare land, and stockpile classes. We can also look at turbidity monitoring and other symptoms of mining. And we'd also like to develop a graphic user interface or a GUI to allow our colleagues within the relevant regulatory authorities and enforcement authorities to be able to easily access this tool and to be able to use it in a more intuitive way without too much need for code. And then through that, we'll also have capacity building and skills sharing to be able to do this monitoring and this regulating using these science-based tools. So with that, I'd like to say thank you very much and acknowledge some people who were involved in this work. Alex Leith, our colleagues from Digital Earth Africa, including Edward Boama, the Tikina Daosamu and the provincial officers, conservation officers, Jay Bao Vuli, Mrs. Tarosila, and the Matini Tikina, Mr. Tamailai, and Tranikoro, as well as Gary Lee, Kishan Kumar, and wider colleagues from the Mineral Resources Department and UNDP. Thank you very much.
Okay, then we just go to the next winner, and also congratulations here for the winning, which is the second place, and the second place is going to Ashwati Mundayat. And I'm very happy that Ashwati she's from is from International Institute of Information Technology, and will present us now his presentation about this mini project. Please, can you just come up with your presentation?
Share my screen.
Yes, please.
Screen visible to everyone?
Okay, for me still it's loading.
Let's see.
Correct. Is screen visible? Is the screen visible to everyone?
Yeah, no, still not. It's still loading. Sorry, we can't still see it.
I have shared my screen.
It could be a bandwidth issue. Maybe you can turn your video off for a moment and then see if it
Yeah.
comes up. No, still no.
For me, it's showing the your screen sharing. I'll stop the share and share it again.
Okay.
Okay. Sorry, yeah, we still don't see it.
I'm sorry. Yes, I'll try once more.
Just try it again.
I'll try rejoining the meeting once more.
Okay, so you like to disconnect and then to rejoin? Okay, because then I think the best probably would be, I don't know, if you try to solve these connection problems, then I would probably go to the next.
In the meantime, you can also email it to one of us and then we can run it over for you.
Okay, there's still somebody saying that he can or she can help you, which is somebody else. I'm not sure. Okay, so then I would suggest again that we go to the next presenter, and you just try in the meantime to resolve this connection issue. I'm sorry, Ashwati, but probably you can try it. Oh yeah, now I see something.
Is it visible now?
Yes, I see your screen now. It's
Yeah,
it's still not in the presentation modus, but it's there. Yes. Great. Very good.
perfect.
Now it's visible, right?
Yeah. Thanks.
Delay. I will start my presentation.
Yes, please.
So
Please just start.
yeah. So my topic of my project proposal, which I submitted for this competition, is change assessment in machine learning based multi-hazard susceptibility maps in the Hindu Kush Himalayan region using piecewise regression model. So through this slides, I'll try to explain the motivation for selecting this particular topic, what was the objective of my project proposal, and the background from which the work started, my methodology, and my preliminary result, and how I'm going to take this work forward. So Hindu Kush Himalayan region is one of the region it is very prone to natural hazards because of its steep terrain, heavy monsoons, and active tectonics. And for my proposal, I chose the area Nepal, which is located within the Hindu Kush Himalayan region. where frequent landslides, floods, and earthquakes are occurring because of excessive rainfall, glacier melt, etc. And one of the factors, along with the ecology of the region, is the anthropogenic factors like land use, land cover changes, urbanization, deforestation, etc. So most of these hazards, when we look at from a perspective, it doesn't occur individually. It occurs one after other as a cascading manner. But most of the existing studies, we only focus on as a single hazard, how it affects and which areas are more prone to. We're not looking in a perspective of how multi-hazard, how a cascading manner, one hazard will lead to the other hazard. So through this project proposal, I'm trying to understand that aspect. So through this work, the major focus of the sustainability development goal, which I am focusing, are sustainability development goal 11, which is sustainable cities and communities, and SDG 13, which is the climate action. So through this work, what I'm trying to give my contribution to the community is to these multi-hazard susceptibility maps will help us for urban planners to have a better city and better urban planning and to take a climate action implementations like early multi-hazard warning systems. Major project objective of this proposal is to develop a machine learning based multi-hazard susceptibility mapping framework for landslide and floods in Nepal. We are using two major types of fusion methodology, early fusion and late fusion approaches. We are incorporating multi-year hazard inventories to track how each year hazard inventory helps us to improve the susceptibility mapping, and we are generating a dynamic data-driven map so that it will help for urban planners and for early warning systems to understand how we can reduce the disasters and for early mitigation plans. So the background for this study started from an initial study which we conducted in the southernmost state of India with Kerala, where we studied individual hazard, flood hazard susceptibility mapping. So most of the existing studies focusing on small regions, and we are implementing a single model for the entire region. So from my study, what we implemented in the state of Kerala was we divided the study area into two spatial levels. So initially, we divided it into ecological sensitive zones, how sensitive each of the parts of the Kerala for various disasters. So eco-sensitive zone 1 to 3, that's the first level of spatial partitioning. Then second level of spatial partitioning to implement the quick prediction of susceptibility values, we divided our study area into square grids. So through this, we were able to generate an susceptibility map for the entire Kerala. But a few of the shortcomings which we found in our study was that since all of these grid-wise we were doing the prediction, we were having edge artifacts around the grids. And through this current project proposal, we are trying to avoid the edge artifacts which we earlier found in the existing study of Kerala, and also to implement this study which we earlier conducted for the state level to a national level for the entire Nepal. So the major workflow is initially we are generating from the existing inventories, and through the satellite imageries, we are developing the training data set, and we are choosing the best features based on the literature reviews and the selection based on various feature selection methods like sharp value and VIF. And as I told earlier, the novelty of our method lies in the two-level spatial partitioning. So we are having a grid tessellation so that for the ease or to increase the speed in computation of the susceptibility values, and eco-sensitive zones or different zoning or NNH zoning per grid we are doing so that spatial heterogeneity of the study area is considered, and we are not using one single model for the entire study area. And then we are doing the multi-hazard modeling. So here, as per my proposal, we are doing two approaches, late fusion approach and early fusion approach. The late fusion approach, which is in the existing most of the studies, we are modeling individual hazards separately and finally fusing the maps together. We're not considering the correlations or the uncertainties of cascading effects of multiple hazards, the late fusion approach. In the early fusion approach, we are doing a joint modeling approach, and we are using DAS and PySpark to parallelize the predictions across the grids. And finally, We are merging the grids using the inverse distance weighted interpolation method and generating the multi-hazard susceptibility mapping. So the major data set which we have used across for this study are the digital elevation model, Sentinel-1 and MODIS data set for the flood inundation map, glacial lake inventory, and the church daily data set for precipitation temperature and glacial lake distribution. And for soil type and land use land cover, open land map and world cover 10-meter resolution dataset, global gridded landslide inventory dataset, and resolved ecoregion dataset. So all of this dataset we have brought the resolution of 100-meter for the susceptibility map generation for the entire Nepal. So these are the few of the highly important driving factors which we have implemented for the studies, which are land use land cover, proximity to glacial lakes map, elevation map, and soil class map. So as I told earlier, we are doing a two-level spatial partitioning, and we got the two-level spatial partitioning map. Initially, we got it from the eco-region maps of Nepal. So these are the few of the eco-region maps of Nepal and conservation zones. So, as per the resolved dataset, Nepal is into conservation zones, NNH0, 2, 3, and NNH4, which is not covered in any of the previous NNH zones. So, NNH zones are nature needs half zones. So, those zones means that those each of the 0, 2, 3. So 0, it has high level of protection, and 3, it has very low level of conservation, biodiversity protection exists there, and more human interactions or human changes like deforestation, urbanizations are happening highly in those regions. So here, so these are the 4 of the zones which we have used to compute or to understand or bring the spatial heterogeneity of our study area into multi-hazard susceptibility mapping. And here, to speed up the prediction, we have divided our study area into square grids. So earlier, for our initial study of Kerala, which we have done earlier, we have used non-overlapping squares, which gave us edge artifacts, as I said earlier. So here for the Nepal, what we have done is we have done overlapping square grids, which we have an overlapping in all the 4 sides, so that we can reduce the edge artifacts when we are finally computing the entire susceptibility map for Nepal. So next is the late fusion approach. For the late fusion approach, we are individually modeling for flood and landslide for different models. So here we have implemented random forest, XG2s, and light CDM models using multi-output wrapper for the late fusion approaches. Then for the earlier fusion approaches, so through the earlier fusion, we are trying to jointly model for flood and landslide susceptibility. So for that, here we have implemented custom loss function using multivariate Gaussian. So we are assuming that the susceptibility value existing in our study area will follow a Gaussian distribution. So we are computing based on the mean or average susceptibility value of flood and landslide and the covariance matrix, which consists of the uncertainty and correlation between the flood and landslide to give the final susceptibility values across each point. So for each point, we'll get a flood separate point, a value, and a landslide separate value. And finally, we are running the susceptibility mapping using DASK. So here we have used DASK, and we have done each grid as a unit of worker to do the parallelization of our entire final prediction workflow. And finally, after predicting for each data point in the each grid, we are merging the final map to do the inverse distance weightage merging. As I said earlier, the inverse distance weighting merging will help us to avoid the edge artifacts, and we are finally computing the susceptibility maps. So this is the multi-band, multi-hazard susceptibility map. Here, red red color indicates the flood-prone regions, green color indicates the landslide-prone regions. And the fusion of colors of red and green, like yellow, orange, or dark brown, those indicate the multi-hazard approach. Here, this is the random forest approach. You see that we are seeing very small regions which are marked as yellow, orange, or dark brown or such colors. Most of them are marked as the individual hazard zones because they are having individual learning, independent learning. There is no joint learning happening. But when we are doing a multi-layer perceptron with a custom loss function of multivariate Gaussian, we are getting most of a few of the regions as colors or dark focus. The question will be, how can we say that the early fusion approach is better than the late fusion approach? So as we can see, the most of the southern regions in the Nepal are the plain regions, middle regions are the central hill region, and north are the high Himalayas. So based on the driving factors which we have considered, like population, slope, etc., the northern regions are having predominantly very low hazard occurrences chances because we have considered population as one of our driving factors. When we go to the middle and the southern region, it is having more of the mixture of colors of yellow and dark yellow and orange color, which indicates that floods are more prominent and landslides both co-occur in the southernmost region of the Nepal, and the mid hills are more prominent to landslide, and some patches have shown which occurrences of both and flood alone. And how we are going to take this work forward. So right now we have done the inventory mapping for 2000 to 2020, and we have generated the susceptibility map. So for going forward, we are trying to take this particular map which we generated as an input factor and generated yearly base map for the 2020 to 2025 yearly multi-hazard susceptibility map for the entire Nepal with a 100-meter resolution. And along with that, we are trying to implement that entire setup in an interactive dashboard manner and expansion of this entire setup for the other hazards. So Nepal is more prone to earthquake as well. So right now we are only implementing 2 hazards. When 3 hazard comes, how the visualization changes, how we can implement it as an entire framework. We want to move towards that. So I would like to thank my professor, supervisor, Professor Jaya, for her continued support and for guiding my work, and my lab members for their encouragement and for the support throughout this work, and my college, International Institute of Information Technology, Bangalore, for providing me with the academic environment to, and the computational resources to conduct my work. Thank you.
Yeah, thanks a lot, Ashwati. Congratulations. A very, very good, let me say, presentation. And also you deserve really the second place. So thanks a lot for this. And even after having some difficulties, technical difficulties, now here the presentation went very good through. Thanks a lot. And congratulations to your second prize. Okay, let us go then to the first prize of this EO4SDG Mini-project competition. The first prize is going to Jiang Di. So Jiang Di, she's already here, and she will present you the results entitled of her project works, which are related in principle to glacial lake mapping under climate change, a novel solution using remote sensing foundation models. So Jiang Di, you're open to share with us your slides.
Okay, thank you for Irina. And can you see my slides?
Yes, we see them.
Okay.
Great, perfect. Everything is fine.
Hello, everyone. My name is Jiang Di, and I'm very delighted to be here to give this presentation. First, I'd like to thank all my co-authors, Xi, Irina, and Adnan. Without your contributions, we could not receive this honor. And today I will give a presentation on topic of glacial lake mapping using remote sensing geofoundation model. At the beginning, I'd like to address one question. Why does accurate mapping of glacial lake matters and how it related with the sustainable development goals? First, as we can see from the 2 figures on the left, the glacial lake are increasing rapidly during the past 4 decades. And it has a very close relationship with the climate change, which directly influence the climate action decision, therefore influence the SDG 13. And also, the increasing numbers of these glacial lakes represents a growing source of fresh water, which directly contribute to the clean water and sanitation of SDG 6. Furthermore, the glacial like outburst floods will pose some potential risk to the downstream communities with the sustainable cities and communities of SDG 11. Therefore, accurate mapping of glacial lake has very essential for the development goals achieved. And here, normally the researchers, they use two types of data to extract or map the glacial lakes. One is optical, which performs well in clear sky conditions, but it struggles when the glacial lakes are covered with snow or ice. And the synthetic aperture radar, which is SAR, can penetrate across and work at all weather and all day conditions, but it still have the problems because it's complex backscattering mechanisms. And here, there are more and more studies that use multi-sensor fuse data to combine the pros and cons of both optical and SAR. Here we still face a lot of challenges. For example, the first one is we don't have so much enough label training data for the multi-sensor fusion data. It means that the data we used for AI-related training is not enough to support. And the second one is, as we can see, the glacial lake has different shapes, and there are a lot of similar features will disturb the extraction or mapping of these lakes. And therefore, especially in the mountainous areas like the high mountain Asian areas, the complexity terrain will disturb the image extraction. To tackle this, we introduced the PRISV geofoundation model. The reason why we use PRISV here is that first, it pre-trained with Harmonos landside and Sentinel-2 multispectral data. This data size is more than 4.2 million images. So it's pre-trained with a very large data size. It gives the model ability to have a general purpose understanding of most of the natural things in satellite image. And besides that, the PRISV is self-supervised with vision transformer architecture. This architecture make it very flexible to different model and can be adaptable to different downstream tasks or fine-tuned to different segmentation tasks. And here, these two advantages make it more useful in large-scale glacial lake mapping. And in detail, we introduce UVIT model as our method in this project. The UVIT model, it has three key components. The first one is U-shaped like encoder and decoder structure. And this structure is the seem like the unite, but in the encoder, we initialize the original encoder with VIT backbone and initialize it with PRISV weights. And the decoder is just like unite decoder for upsampling. And the second part of this UVIT is first layer. We can see that clearly in the first layer, we add two block. The first one is enhanced squeeze excitation block. This block make this model to align the input bands with the pre-trained PRISV parameters and improve the data fusion. This means that our method is very flexible to different types of data with different combination of bands. And besides that, using the inverted bottleneck block in the second part of this first layer, it is a lightweight CNN model to extract local features, which can in some way complement the vision transformer model for global feature extraction. And to implement our methods, we choose two study sites. The first one is North Pakistan. In the North Pakistan, it is multi-sensor fusion data combines the 4-band image from Sentinel-2 data and 1 VV band from Sentinel-1 SAR data. And in the West Greenland is a SAR-only data size, which we gain this data size from Golfin 3 data. And here we show the results between these two different data sites. And we can see clearly here we conduct a comparison of different models that we normally used in the glacial lake mapping, including the UNet Deep Lab V3 Plus and MA-Night. In the multi-sensor fusion NPK dataset, we can find out that our proposed methods shows the highest F1 score, but in the SAR-only WGL datasets, it does not perform so well. And here, because our method works well on the multi-fusion data size, so to better evaluate, we compare it with the public data size. The public data size we use here is from Landsat. To keep the comparison, we choose the data size. We choose the data that we gained from the same day to make sure that the results are kind of comparable. And in detail, we can find out that from, for example, in the second columns of these figures in B and F, there are some outlines. The red line represents our results, and the blue line represents the public data size. Here we can find that there are some shadow that regarded as glacial lake in the public data size, but in our methods, we clearly define it. And besides that, our methods works well in small lake extraction. Here, as we can see from the figure D to F, there are a lot of small lakes with areas smaller than 0.001 kilometer square can be detected by our methods. And also in the figures G to I, we can find out that even in the cloud conditions, our methods performs well because we introduced the SAR data. And in summary, our results shows light and false negative results, and it can work well in the shadow interference. To measurements that our the module we introduced in the UVIT is useful. Here we conduct some ablation studies. First, we replaced the modules with other block. For example, here we replace the enhanced squeeze excitation block with band copy, a BB block with convo block, and VIT encoder with UNet encoder. We can see that compared with the original F1 of 0.89, the ablation of each module will decrease compared to the original one. And besides that, because we use the multi-sensor multi-fusion data, we want to figure out which bands we put is more important in this glacial lake mapping. So here we conduct the experiments for different band combinations. The results show that the near inferior band is the most important band in the glacial lake mapping, and the red band is the least important. And as we mentioned before, we talked that our model does not perform so well in the SAR-only WGL data size. Here we will explain detail why it caused that. Here, we replaced the GeoFoundation model with another large pre-trained model, VIT-ME base. The difference between this pre-trained model is that the PRISV was pre-trained with multi-spectral data, and the VIT base is pre-trained with the ImageNet 1000, which is the RGB image. And compared in its two data size, in the NPK data size, the PRISV performs better than the VIT base because the PRISV is pre-trained with multispectral data, and the NPK data size have the bands of multispectral bands. And in the WGL datasets, the VIT base is better. This is because that here we use the false RGB image, which combines from the HH and HV star image in the WGL datasets. And the VIT base is also a RGB image. So the similarity between the pre-trained datasets with the datasets we used in our methods leads to the difference performance in these two results. And it also tells us that we need to develop a kind of star geofoundation model. It can further improve the model generalization. And at last, because our methods is based on the geofoundation model, it's pre-trained with a very large data set. We want to find how it will behave in the small data size. And here we reduce the input portion data size in our data. And when we reduce the data input portion to 30%, the iPhone score only decreased 2.2%. This means that our method performs well in the small data size. And in summary, we propose a UVIT model using the PRISV for the glacial lake mapping, and it all performs on the NPK data size, which is the multi-centrifuge data size, but it's underperformed in the cell-only WGL data size. It's likely due to the similarity between the pre-tree data with the data we used in the fine-tune task. And also, our method shows a robust performance with reduced training data. In the future, it's better to develop a more general benchmark data size for glacial lake mapping, and more comprehensive or evaluation should be conducted to better compare the advantage of these methods. And also, it's important or essential to develop a large pre-trained model using SAR data. And that's all of my presentation. Thank you for your listening, and I'm happy for your questions. Thank you.
Okay, great. Yeah, thank you. Thanks a lot. And congratulations again for the winner, for the first prize of this EO4SDG competition. So thanks a lot. It was a very comprehensive presentation. And it has it will have a big impact. We wish you all the best for the future, Jangdi, and hopefully, yes, you will stay in the research domain and make further research on these topics. Great, and thanks a lot.
Thank you.
Okay, let me try again to share my screen if possible. Yes, it's going then forward on. And would hand over now to Muad Khalid, who will present now the winners of the Earth at Risk image contest.
Thank you, Rina. So I'm glad to announce the award recipients of the third edition of the image contest, Earth at Risk, organized by the IEEE GRSS Young Professionals and React Technical Committee in conjunction with the Mini-projects for Sustainable Development Goals competition. So you might be aware, the contest aims to raise awareness of nature and climate crisis and to demonstrate the power of Earth observation data in helping us better understand the environmental changes on Earth and find solutions to protect our planet. A big thanks to all the participants. We received 45 submissions. Do you mind? Yeah, thank you. We received 45 submissions across nations, which is an achievement to see such an increase in the number of submissions from the previous editions. Yeah, next slide. And also we are astounded by the quality and diversity of the submitted Earth observation data images, highlighting different environmental issues in this version of the contest. Moving forward, I would like to thank the evaluation committee a very heartfelt thanks to Dr. Jacob, affiliated to University of Graz, Austria, Himalayan University Consortium, and Professor Irina from the Public University of Zurich and German Aerospace Center for being part of the evaluation committee and supporting the YP in this edition of the contest and also the future editions. So moving forward, let's congratulate the third place, Mohammed Bilal from United Nations Development Program. Bilal, do you wanna share your screen?
Yeah, sure. I can share my screen. So, but right now I'm seeing the wrong. Okay, yeah. I can see. Just a sec. Okay. Okay. You guys see my screen?
Yes, Bilal, we can see your screen. Please go ahead.
So yeah. First of all, thank you so much for like awarding me third place in the image at risk contest. So I will quickly go through the presentation. The topic of the submission was it's the crowded and the joke in the city of gardens. I will explain why I choose this topic, especially for the study area that I represent some of the visualization. So quickly about me, I'm from Pakistan. I have completed my initial education, my bachelor's, and have done some of the work in geospatial domain in Pakistan. Back in 2022, I got the Erasmus Mundus scholarship to pursue the master program called Copernicus Master in Digital Earth. That is a basically consortium of two universities. That is Paris London University of Salzburg, and the other is Plask University of Olomouc. After completing the master's, I got into different internships. Currently, I'm working as a geospatial intern in the United Nations Development Program. And the interesting fact is that I'm a football player and also a traveler. So, as far as my education is concerned, as I said, the bachelor is from Pakistan. I completed the first year of my master's in University of Salzburg and the other years of master's specialization in cartography in the University of Olomouc. So jump into the main submission that I submitted for this contest is the called Crowded and Choked in the City of Gardens. The aim of this research is to basically visualize the alarming situation or the decline in the study area that is Lahore, the air quality for over the past 2 decades. So in order to visualize this, you can say decline in the air quality, I use a remote sensing product that is called SAT PM 2.5 that I will discuss in the further slides. And along with that, I visualize the population distribution, that how many people with different age groups is affecting due to the rapid increase of these air pollutants. So the city of gardens is basically called Lahore. It's like famous because it has a lot of Mughal Empire heritage, a lot of gardens and stuff. So that's why it's called the city of gardens. And the choked is increasing the pollutants yearly basis. So that's why I titled the crowded and the choked in the city of gardens. So the study area, let me dive into more about it. The study area, the Lahore. Lahore is located in the northeastern part of the Pakistan that lies in the Punjab province with our 13 million population. Every year, this city faces a air pollution crisis due to different activities, majorly contributing the biomass burning, industrialization, and as the changing climate patterns that cause different you can say trapped of pollutants in the air, especially the PM 2.5. Why PM 2.5? I will like explain in the further slide why it's more dangerous to the people who is living in the region. And according to the WHO, the PM 2.5, the particular matter, increased 99.5 microgram per meter cubes, that is 20 times higher than the normal rate in a city back in 2023. That is, you can say the alarming statistics that the law has faced. PM 2.5 is one of the pollutant that is 2.5 micrometers smaller in size, that is easily inhalable pollutant. It can directly enter into the lungs and the bloodstreams that got a lot of problems like heart strokes and the choking situation. The people who lived in those areas. The main cause of this pollutant is basically the fossil fuel burnings, the biomass burning, and the other anthropogenic activities that is happening currently in the city of Lahore. The data is used to represent this particular matter, PM 2.5, on a ground level. I use SAT PM2 dataset, that is a combination or derived dataset of multiple satellite sensors that include MODIS, MISR, and the VIRS, other the products. So it is basically provided by the Atmospheric Composition Analysis Group based in Washington University. They provide the monthly and annual data set of this concentration at the ground level for approximately the 1 kilometer square spatial resolution. So I utilize this data set for the visualization or for the visualization of concentration, or specifically the PM 2.5 at in Lahore. And along with that, I use the population statistics that I acquired from the Pakistan Bureau of Statistics to analyze how much of different age groups is affecting due to the increase of this pollutant in Lahore. So the method I adopted is basically the visualization method. I drive the product, like downloaded the product from the website, or do some pre-processing in terms of the normalization, in terms of the color scheme, and then I overlay the population statistics that I downloaded from the Pakistan Bureau of Statistics to analyze each year how many age group distribution is affected by this pollutant. So, and then I compile this data set into a GIF maker to analyze the trend, to analyze the temporal evaluation of this PM 2.5 concentration in Lahore. So that was the end result to see how year by year, this is the 20-year of decade. So I think, yeah. So this is a 20-year of duration that I'm trying to visualize. I try to visualize to see how many different age groups of people in Lahore is affected by this majorly contributing pollutant in Lahore region. And mostly it has been seen, like through this analysis, the children and especially the age group of 25 to 64 people are more exposed to this kind of pollutant. So yeah, this visualization is basically in order to raise awareness to like allow people to see how these pollutants or these kind of activities raises this kind of concentration and how many people of different age group is affected in that specific region. So yeah, that's all on my side. Thank you. These are the references.
Thank you, Bilal. Thank you so much. So for the second place, we have Odilami Oluwabumi from the University of Lagos. Congratulations on receiving the second place in the contest. Probably you can share your screen, Odilami, if you're there.
Give me a minute to share my image.
Yeah, sure.
Otherwise, I can just pop it up again if it's only the image, if you like. I can also share
Yes,
it.
I'll be showing the image only, and I'll be
Okay,
talking
then I
about
will.
it.
Then I will share it. That's perfect. Not a problem.
Can you see my screen? Hello?
Can you see it?
Can you see my screen?
Yes.
Okay, that's good. Thank you. Once again, I would like to appreciate the organizer of this contest, that is IEGRS, for awarding me the second position in this contest. and I really appreciate it. So the topic of my image is heat risk distribution across Kano metropolis in Nigeria. And this image is important because urban area continue to expand rapidly. And it is important for us to understand the spatial patterns of its vulnerability because it is essential for public health planning and urban development strategies. So that's the motivation behind this image. So I created a comprehensive heat risk index to identify most vulnerable communities within Kano urban area. So for the remote sensing data source, I utilize three primary sources, three remote sensing platforms. The first is the Landsat thermal sensor, which provides a land surface temperature that was used for this image. So it forms the foundation of the heat assessment because the Landsat 8 thermal sensor measures the land surface temperature of the Earth, and it has a 30-meter resolution. And the second data source is the Sentinel-2 image, which was used to classify the land cover that was used to derive the lack of tree canopy within the Kano State metropolis. And the last data that was used is the world pop data, which provides the population density. It provides the population density estimates using satellite sensor. So at the end, by combining these three remote sensing sources, I was able to derive three variables. And the first variable is the lack of tree canopy. So for each ward in the Kano State metropolis, it shows the lack of tree canopy in percentage. So some ward lack up to 98% or 99% of tree canopy. So that means there's no tree that provides shade for this metropolis. Also, the second index or the second variable rather is the maximum land surface temperature. So this second variable shows the maximum LST in each ward, and the lowest maximum temperature in a ward is 34.6 degrees Celsius, and the highest in a ward is 44.52 degrees Celsius. And lastly, the third variable that we use is the population density. So this shows where we have more people living. So from the image, it is clearly shown that most people lived in the center of the Kano State metropolis because this was has the highest population density, whereas the outskirts of the Kano State metropolis has a low population density. So we have more people living in the center of the metropolis. So by combining these two, by combining these three variables, I was able to derive the heat risk index of Kano State metropolis. So a weight of 1 was assigned to the lack of tree canopy. Also, a weight of 1 was also assigned to the maximum temperature, and a weight of 2 was assigned to the population density. This is to emphasize on area where people actually live and work. So this weighting strategy ensures our index prioritize human exposure rather than simply identifying the hottest location. So I wanted to focus on where we have more people living. So that was the reason a weight of 2 was assigned to the population density. So the key findings that was discovered in this image is that the highest risk area within the urban center at the Zongo ward, Kantudu ward, Yawa ward, and Dongo Nama ward. So this ward has the highest risk index because they have a very high population density, and also they are experiencing a high degree of land surface temperature. So this particular words require urgent intervention. Interestingly, the outskirts of the metropolis shows a very low to low risk level. So that means the outskirts of the area did not really experience high risk index. So these findings have a significant implication for urban planning and public health policy in Kano State because the concentration of high risk area in the city center suggests urgent need for its mitigation strategies and particularly increased urban forestry and green infrastructure developments. Moving forward, the heat risk index provides a baseline for monitoring changes over time and evaluating the effectiveness of cooling intervention across Kano State metropolis. Thank you for your attention. That's all.
Thank you, Abdulami, and thank you for putting so much hard work into this well-deserved second place. Thank you.
Thank you.
Moving to the first place, we have Aditya Sin, Jayendra Sin Parmar from Geospatial Engineering Group, IIT Roorkee. Congratulations for the first place. Do you want to share your screen or is it fine if we share it from here?
Thank you, Khalid. I will share it.
Sure.
Is it pretty visible?
Yeah, it's visible.
Now?
Yeah, it's visible. Yeah, please go ahead.
Okay. My submission for the Earth at Risk contest was like, I used to watch news about the Israel and Hamas war that was going on during that period. So I thought of like, war just don't affect the humans only. It can affect the ecological and environment of the surrounding region also. So I did do a study on this, like getting the impact of Israel-Gaza war on the vegetation health. And in the news, we generally say that there are images being circulated of missiles being fired. They are getting misfired at some place else. The buildings are getting damaged, the fire, the chaos, and the lives affected by that war. But what we don't generally see in the news is the study topic today. And before war, the Gaza's agriculture was booming quite very well, and it was very diverse and productive farming. And they had various crops like strawberries, citrus fruits, olives, dates, and tomatoes. And the agriculture was self-sufficient, and it was providing the food security for the region. And it also used to make a significant amount of exports and support the economy of the Gaza and the people living there. But in this study, I did use the Sentinel-2 dataset and the post and pre-war imagery, and that is July 2023 and July 2024. The war started around like October 2023. And the methodology that basically I followed was I did acquire the image and did cloud masking, and then I did calculate the NDVI. Why I chose the NDVI is the NDVI is a very standard vegetation index, which like literally gives us the health of the vegetations in the over the land. And I basically used this NDVI and visualized it and compared the pre and post imagery. This was my submission, and as you can see, like in the July 2023, the NDVI is a very good. NDVI shows a higher value of, and so we can see the more greener region. And in the snapshots that I have attached with it, you can also directly see that the farms are present over there. But in the July 2024 image, you can easily identify, like you can see it clearly, like the vegetation has grown from very good booming agriculture to like the farms are damaged totally and the soil might be degraded. And the most of the significant amount of damage was in the North Gaza and the Gaza region, and then starting the Deir al Bala and Khan Yunis and the Rafah region. And we generally see that the damage of war is just to the infrastructure and human lives, but the silent damage of war is to the ecology and the vegetation of that region also. Like we can see the 60% of the Gaza's vegetation was damaged or destroyed, and the continuous bombardment and missile strikes have like degraded the soil fertilities, because the ammunitions used by the both the armed militaries are like might have phosphorus in them, and it literally degrades the soil. And most people now, as we can see, don't have enough food to survive, and they need to they are getting help from all around the world by the food aid. And the blockade of the Gaza has also affected, like restricted the import of the seeds and the fertilizer, which is like very essential for the agriculture sector. And the irrigation infrastructure was also lost in the bombardment and the missile strike. And this was my submission. If anyone have any question, and you can further click on this link if you want. I can share my PPT also for the resources. Thank you.
Thank you, Ditaraj, for the presentation. And again, congratulations for the first place. This is a very the topic you have selected is already been highlighted in the media, and we all know how things are with wars, and it's not good for both the parties. We hope things go well with them. But thank you again for participating in the contest, and congratulations for the first prize.
Thank you.
So moving forward, I would thank everybody for joining the call today, and presenting uh, presenting your projects, your contest submissions, and to the React committee for taking the lead on organizing this award ceremony. Special mention to Irina for for everything that has been done for today. Thank you so much. Over to you, Irina.
Okay, yeah, thanks a lot to all the participants. I really appreciate your time, but also your submission. It was actually it's a great effort to do this, but at the same time, it's also great to get acknowledged about it. Having a principal winning a prize is something that is really great. So it means. It is a good sign. It means also you should proceed on this work. It makes sense that you do this research independent under which conditions. So that's great. So therefore, I like again to thank everybody here to have participated today here, and also the participation not only from the winning team, but also the people which are just listening to it. So thanks a lot for your participation, for all the audience. And I wish you still a nice day or a good evening or a nice morning, wherever you are in the world. Yes, and hopefully to see you again in some of the webinars or even other occasions where we have GRSS activities. Thanks a lot, and hopefully see you soon somewhere. Bye.